Welcome to practice number 102. This is the second part of our sawtooth riblets on low Reynolds number airfoil aerodynamics. Part one was podcast number 101. So if you haven't listened to that yet, go back and listen to that and then come back to this. So we're going to pick up where we left off in the last podcast on page 10, where we're looking at the effects of riblets on with different lengths on the aerodynamics of this airfoil. So let's just quickly recap what this is. First of all, riblets are these little jagged, in this particular case, they're triangles, they're isosceles triangles, and they're placed on, in this case, on the upper surface of a NACA 4412 airfoil. And they pitch this airfoil at different angles of attack to see how these riblets affect the aerodynamics, so the lift coefficient and the drag coefficient to be exact. And they have different lengths and heights for these riblets. So they have two different systems. The first one is where they have the height of these riblets at just 1 millimeter, constantly at 1 millimeter, and then they place it over a longer or shorter period of the airfoil. So between like 20% of the airfoil and 80% of the airfoil, even less than that, I think 5% of the airfoil to 80% of the airfoil. But between 5 and 10%, they found that in the last podcast we covered, there weren't a lot of effects. So really above 20% is when you start to get effects, and we'll see this again in this podcast. The other type of riblets that they were looking into was where they held the amount of the airfoil coverage, a certain amount, 50% of the chord to be exact, and then they changed the height of the riblets between 0.6 millimeters and 10 millimeters, which 10 millimeters is huge, especially for an airfoil this size. So, and according to also considering the boundary layer as well, which is an important factor, how much of the boundary layer the riblets take up and how much it protrudes out, definitely affects the aerodynamics. We don't cover it in this podcast, in this paper at least, but if you want to look at other papers, for example, you'll see it again there as well. And this is well known for riblets, which have been investigated for decades. So we'll continue on now with the effects of riblets with different lengths. So they keep the same height at 1 millimeter, and these effects on the lift and drag coefficients. So in figure 7, we see the variations in the lift and drag coefficients of the configurations with different lengths obtained by the surface integrations. So if you're looking at this on YouTube, you can see the video. If you're looking at this on Spotify, you can also see the video. But if you can't, then you can always go onto our YouTube channel and just see the video there. So the L denotion, like the L letter in front of the number, so L5, L30, L70, just to refresh your memory, that corresponds to the amount of the airfoil that these riblets cover. So L5 means 5% of the chord, L80 means 80% of the chord. And figure 7 and figure 7A and B show the difference in the lift and drag coefficients respectively compared to the baseline case, which is a smooth upper surface. These riblets are attached to the upper surface, not the bottom surface. They're typically put onto suction surfaces, so typically upper surfaces for airfoils. If you're using an airfoil to produce downforce, then you put it on the underside, which would then be the suction surface anyway. The pressure side, you rarely put riblets on. In fact, I'm not aware of any studies that have looked into this. So anyway, the lift and drag coefficients are both affected by the riblets at angles of attack between 0 degrees and 12 degrees. The variations in the lift coefficient are acquired by the L05 and L10 schemes, so 5% and 10% of the chords are negative. So these two riblet configurations slightly reduce the lift coefficient. So I should specify that even though they've said that they reduced the lift coefficient, it's by almost nothing. Like if you look at the graphs, you can barely notice a difference. So that's probably in the error. So we can't really conclude that completely, but they are not performing nearly as well as the other configurations, and they're like between 0% and minus 0.2% perhaps reduction in lift coefficient. So they say this suggests that a small riblet length is disadvantageous to the airfoil lift coefficient. So that makes sense if you want to affect the flow of something. Often the more of a flow control device you use, the more effective it will be up until a certain point, and then it often becomes disadvantageous. But in this case, you want to have more riblets than just 5% or 10% of the chord being covered. When the length exceeds 20% of the chord, the lift coefficient augmentation is increased with increasing length. So in other words, the more riblets you put on, even up to 80% of the chord being covered, you still get a lot more lift. So that's quite amazing. As the length reaches 80%, the considerable growth of the maximum lift coefficient is up to 17.5%. That's huge. So to give you an idea as to how good a flow control device is, if you can get like 3% increase in lift coefficient without any drag penalty for an airfoil, that's considered really good. To get 18% almost is unreal. Like that's, you don't get that in many situations. So meanwhile, the effects of the riblets on the lift coefficient is also affected by the angle of attack. When the length of the riblets are between 20% and 50% of the chord, the augmentation of the lift coefficient increases with the increase in angle of attack. So in other words, when you have like a moderate amount of the airfoil covered with riblets, increased angle of attack effectively linearly increases the amount of lift that you will get. So it's that's quite nice. However, when the riblets exceed 70% of the chord, performance at small angles of attack and large angles, the performance of these riblets at smaller and larger angles of attack are better than medium angles of attack. So in this graph, you can also see that with the L70 and L80 schemes where you have 70 and 80% of the chords covered, at low angles of attack, so 0 degrees and 2 degrees, you get between 7.5% and 12% increases in the lift coefficient. When you get to 6 degrees, that drops down below 7%. Then when you go back up to 10 degrees, then the lift coefficient increase, it goes up again. So it goes up to like, as I mentioned, 18% almost. So figure 7b shows that a portion of the designed riblets with various lengths induces a lower drag coefficient compared to the original airfoil. And this is again amazing because to not only get an increase in lift, but a reduction in drag, that's like the holy grail. So the fact that they've been able to achieve that is very nice. The change in the drag reduction is not constant with riblet length though. When the length is 10% of the chord and the drag reduction capacity of the L10 is worse than for L05. So in other words, for some reason, if you have a riblet length of 5%, the drag reduction is nothing, like it's about 0%. But when you go up to 10%, the riblets cover 10% of the chord, for some reason the drag increases by like 4%. Oh, sorry, no, not 4%, 2%. So there's an issue there. But then when you increase the amount of coverage even greater to 30% of the chord, then you start to get a reduction in drag. So there's this non-linearity there. So they say as well, as this riblet length exceeds 30%, the drag reduction occurs at 7 to 12 degrees angle of attack, and the change in this increase grows exponentially, not exponentially, but grows dramatically. So when you're at 4 degrees, let's say, the riblets are reducing the drag by about 2% on average. When you go to 12 degrees, they're now reducing the drag by like 15%. So that's a massive non-linearity there, and it's very good. When the lift coefficient, when the length is 80% of the chord, the maximum reduction in the drag coefficient is 15%. So it is clear that the performance of the riblets decreases the drag. In decreasing the drag is poor at small angles of attack, especially when the angle of attack is below 3 degrees. The lower drag can only be induced at these low angles of attack by the riblets that cover most of the airfoil, 70% and 80%. If you have less of the airfoil covered by the riblets, you're not going to be getting a drag reduction. As a result, when the length of the riblets is 20% of the chord, the drag reduction capacity increases with the enlargement of the riblet coverage. As the airfoil drag is as the airfoil drag is made up of the viscous and pressure drags, the drag coefficient can be expressed by the pressure coefficient and friction coefficients. So let me explain this a little bit because I've spent quite a lot of my career looking into this kind of thing. So we're looking at a two-dimensional airfoil, or you could call it an infinite airfoil if you want to. In this particular case, they achieve the same purposes. So for a two-dimensional airfoil at low angles, at low speeds, so we're not getting into compressible speeds yet, which means that we're below Mach number of 0.3 by rule of thumb. The drag of an airfoil is comprised of two components, the pressure drag and the friction drag. The pressure drag comes about due to the difference in pressure upstream compared to downstream of the airfoil, and this results in a force because pressure is just force divided by area. So if you know the area of the airfoil projection, then you can calculate the force. The viscous or the friction drag or the viscous drag is due to the flow going over the airfoil, and obviously you have the air on the surface, there's friction there. So that's creating some sort of drag. Now, at low angles of attack, for any airfoil where the flow is attached at the low angles of attack, or I could probably just mitigate this angle of attack bit. I would just say for any airfoil in any configuration where the flow is well attached, then the viscous drag or the friction drag makes up the majority of the total drag. The pressure drag makes up the minority of it. Now, if you have flow separation, that then switches. So the pressure drag becomes the dominant factor and the viscous drag becomes a minor factor. So for most airfoils, this translates to at low angles of attack, viscous drag makes up the majority, pressure drag the minority. At high angles of attack, viscous drag makes up the minority and pressure drag makes up the majority. So that's just how it translates. So the reason why this is important is because now we can understand how the drag comes about on this airfoil. I just would going to touch upon briefly three-dimensional airfoils because now we get into more practical applications because most applications do use a three-dimensional airfoil. And in this particular case, the drag is now not just made up of the pressure drag and friction drag, but also something called the induced drag. The induced drag is visible as the wingtip vortex. So that's a very easy way of understanding what that is from a conceptual point of view. We're not going to get into it here because I've done other podcasts on it and I'll probably do other podcasts in the future. And then finally, when you get to higher velocities, so Mach numbers above 0.3, you start to get something called wave drag. And this is due to compressing all this air in front of the airfoil and producing shock waves. And then you have critical Mach numbers and all this. So that's another component of drag. But in this particular case, neither the induced drag nor wave drag play a role because the conditions are not right for them. So they're zero. So we're left with just pressure drag and friction drag. And they have an equation here. It looks somewhat complicated, but it's very simple once you understand the theory behind it. So what it means is the drag coefficient equals the pressure drag coefficient plus the viscous drag coefficient, and this so the pressure drag coefficient equals the closed integral over the airfoil surface of the pressure coefficient times by the distance that you're going in the x direction. So it's in the free stream direction. In layman's terms, this means that you're just integrating the pressure over the airfoil and timesing it by the projected area in the x direction, so the free stream direction. That's the drag direction. The viscous drag or the friction drag equals the summation or the integration of the friction coefficient on the surface again in the x direction. So it's quite easy to calculate once you understand it, and the induced drag is somewhat easy as well. But this means that we can decompose the drag coefficient into their components, so we can analyze both of these components to understand why riblets are, or any other flow control device, is having the effect that it's having on the drag coefficient of your airfoil or any other object. So figure 8, let's move to figure 8, shows the drag component changes in the riblets with different lengths. So this is what I was talking about, where you can break up the drag into the viscous part and the pressure part and look at how these riblets are affecting each one and what the overall result is. They say the percentages of the pressure drag in the original drag is positively correlated with the angle of attack under the whole operating condition. So in other words, what they're saying is that for the pressure drag, the original drag, so of the baseline airfoil, has a black mark here as 0, and everything else is correlated to that based on whether it increases or decreases it. And that's what we usually do. And the skin friction drag also has that same situation going on there. The viscous drag plays a more crucial role than the pressure drag at small angles of attack, as I mentioned earlier, accounting for more than half of the total drag. However, the effect of the drag components is the opposite at large angles of attack. That's just because this airfoil stalls at large angles of attack. Therefore, this explains why the performance of the riblets decreases the airfoil drag at various angles of attack compared to increasing at other angles of attack. So at low angles of attack, remember how we said that there was not much of a change, but when you get to high angles of attack, we get a change, a massive reduction in the drag coefficient. This is because the different components of the drag start to come into play, more or less. So for the L05 scheme, so for the configuration of riblets where it only covers 5% of the airfoil surface, although the riblets raise the pressure drag at most angles of attack, the viscous drag is only increased at 5 degrees. contributing to the total drag of the L05 scheme, the whole range being substantially identical to that of the original drag. So in other words, there is a slight increase in the pressure drag, but the friction drag often overrides that, so the net result is nothing. The viscous drag of the L10 scheme, so that when the riblets cover 10% of the airfoil suction surface, increases at angles of attack between 0 and 6 degrees, but then decreases angles of attack between 7 degrees and 12 degrees, while the pressure drag increases no matter what angle of attack is. So consequently, the reduction in the airfoil drag is only occurs at high angle of attack, and it's only by 1.5%. This is probably in the error potentially, but even still, it's almost nothing. So again, these two components cancel out, the friction drag and pressure drag, and this often happens. And the reason why it often happens is because when you try to reduce one, you often increase the other one. So for example, in this particular case, or for pressure drag and viscous drag, pressure drag occurs because of stall. To alleviate stall, to make sure that the flow stays attached, often we try to energize the boundary layer, what we say. This means that we're increasing the velocity of the flow in the near the surface of the object, and this then increases the viscous drag. So on the one hand, we reduce the pressure drag, but on the other hand, we increase the viscous drag, and depending on how much we can reduce the pressure drag, we may get a total drag increase, or we don't know. That's why we need to do testing. And that's effectively what's happening here. It can be seen that the riblets with an appropriate length exert a favorable effect on the viscous drag. When the length of the riblets increases, viscous drag reduction efficiency is entirely superior. So I like that. When you have a lot of riblets, the viscous drag reduction is superior to the pressure drag increase, which is why we get a reduction in the total drag. On the contrary, the pressure drag of the riblet schemes is significantly increased, especially at angles of attack 0 to 3 degrees, which counteracts the viscous drag decreases at these angles of attack, so they cancel out. It is mentioned that the pressure drag increment of each riblet scheme is reduced with the enlargement of the angle of attack. So in other words, as angle of attack increases, the pressure drag of each of these riblet schemes reduces. So it starts off being very, like the pressure drag is exacerbated a lot, is increased a lot at angle of attack. But as you increase angle of attack, this starts to come down. The reduction in the pressure drag at 10 degrees to 12 degree angle attacks is mainly caused by the diminishing separation vortex at the trailing edge of the airfoil. So let's move on to figure 9, where we look at, let me zoom out a little bit so you can see all four. Figure 9 shows the pressure coefficients, the pressure contours, and the streamlines of the original and 3 riblet schemes at 12 degree angle attacks. So the primarily the trailing separation vortex and a tiny leading separation vortex are formed at the original airfoil, which is shown in figure 9a. So we mentioned earlier in podcast 101 actually, that this airfoil produces a small leading edge vortex and a trailing edge vortex, and this trailing edge vortex grows depending on the angle of attack. So when the riblets are arranged at the airfoil surface, the trailing separation vortex of the 3 configurations are significantly reduced. However, the enlarged leading separation vortex are also induced by these riblets. So on the one hand, you're getting rid of one vortex. On the other hand, you're increasing the other vortex. Now, whether these strengths of these vortices are growing or shrinking, you can't really tell just from streamlines. You need to do figure out what the vorticity is, then integrate that over a closed line integral, and then you can figure it out from there. So we may assume that just because the vortex is bigger, it's stronger, but that's not necessarily the case. And an idea of this is if you get a vortex and you just start it, it'll be very small but very concentrated. And then when it starts to disperse, it gets very big, but it's very weak. So the vortex actually diminishing in strength, even though it is much bigger than what it started as. So it can be clearly seen that the pressure coefficients of the original airfoil has a slight bump at 10% of the chord to 13% of the chord. This corresponds to the leading separation vortex. The bumps in the L50 and L70 riblets, so when the riblets cover 50% and 70% of the airfoil surface, are larger than those in the original, and their locations move forward, indicating an increase in the leading separation vortex. So probably the leading edge vortex now, we can say, is probably increasing in strength because we're getting another effect which is growing as well. The pressure coefficients of the riblet schemes on the airfoil suction surface are lower than those of the original, leading to an increase in lift coefficients. So that's how we're getting that there. Just in layman terms, the pressure is just reducing on the suction surfaces of the riblet airfoils, and obviously that's going to increase the lift coefficient. So in figure 11 now, we get to seeing what the pressure is inside the riblets. So they have pressure contours of the L20 and L70 schemes at the riblets. So we're taking a cross section and we can see like a magnified view of them. The pressure difference of these two schemes of riblets at the same location is 0.5 pascals and 0.6 pascals respectively. Considering the fact that the long riblets contain more riblet structures, the pressure drag of the L70 scheme is much higher than that of the L20 scheme and the original. So what we're seeing here is at the, like if you look at the riblet, it's a triangle. At the top of the riblet, so that point, the upstream side of that point has a much higher pressure than the downstream side, but the fluctuation is still only about 0.5 pascals, so it's not a huge amount. Why there would be a difference is because these riblets are effectively a sharp edge, and that's going to induce flow separation. So in figure 12, we now see something really cool. We see the wall shear stress. So I should actually mention their description. So as shown in figure 8a, the reduction in viscous drag is achieved by the riblets with lengths greater or equal than 20% of the chord at most angles of attack. To understand the cause of this reduction, the wall shear stress distributions of the four schemes at locations of 45% of the chord to 56.5% of the chord on the airfoil suction surface at an angle of attack of 12 degrees as shown in figure 12. So in other words, at various points along the airfoil surface, we're looking at the wall shear stress of different riblets compared to the smooth airfoil surface. So what does this all mean and why is it important? Well, the wall shear stress is directly proportional to the friction drag that you're generating. So the greater the wall shear stress, the more friction there is, the lower, the less there is. And by understanding what the wall shear stress is, we can then get an idea as to why the friction drag is behaving the way it is. So they say the wall shear stress changes periodically in every riblet, and the wall shear stress value reaches the maximum at the riblet peak. The peak value is significantly larger than that of the original because of the higher velocity gradient at the location. And that makes sense because you have this point just jutting out into the air, which is going to be at a faster flow, a faster velocity than at the surface of a smooth airfoil. In contrast, the velocity gradient inside the riblet is lower than that of the original, resulting in a smaller wall shear stress value. Moreover, the wall shear stress value near the riblet valley is very close to zero, demonstrating that the fluid is almost static in the valley. The undulating wall shear stress distribution of the riblets was equivalently averaged and is depicted by a dashed dot line in the graphs. So in other words, they're just averaging over the entire airfoil to see how this corresponds to the original airfoil. It can be seen that the equivalent mean wall shear stress on the riblets at this position is much lower than that of the original airfoil. What does that mean? It means that even though you're getting these peaks, like these local maxima in the wall shear stress at the top of the riblets, inside the riblets, most of these areas are at lower wall shear stress values than the smooth airfoil. So if you were to average out the peaks and troughs of what's happening, you actually get a lower wall shear stress value, which means you get a lower friction drag. And that's why we're getting a reduced friction drag. So now we're going to look on the effects of the riblet height, or the riblets with different heights. We looked now at the effects of the riblets with different lengths with a constant height of 1 millimeter. Now we're looking at riblets with heights ranging from 0.6 millimeters to 10 millimeters, and they are constantly over 50% of the airfoil's suction surface. As they say, as the riblets with a length of 50% of the chord effectively improve the airfoil's aerodynamic performance at most angles of attack, the riblets with different heights under this condition are designed in this section. They're explained really their effects. So in figure 14, it illustrates the changes in the lift and drag coefficients caused by these riblets with 5 different heights, ranging from 0.6 millimeters to 10 millimeters. The lift coefficient at each angle of attack is improved when the height is above 6.5 millimeters, and the increase rate multiplies rapidly after 8-degree angle attack. So again, here we're seeing that there's a massive nonlinearity with these riblets where, again, like with the lengths, different lengths of the riblets, at low angle of attack, the effects are not that great, but as you go higher and higher, the effects just become magnified and really amazing. However, the capability of the lift increase gradually reduces as the height increases. So in other words, you reach a saturation point where increasing the height of the riblet no longer increases the lift at all. And this kind of makes sense because you have like this massive thing just jutting out into the air. It's not going to be that beneficial for producing lift and reducing drag. So table 3 shows the change in the drag components and the total drag among the 6 riblet configurations at 7-degree angles of attack. When the fluid passes through the riblet tip, the pressure difference in the riblet increases with the increasing height of the riblet. This contributes to the notion that the pressure drag of the riblet scheme is greater than that of the original, and its amount is in proportion to the riblet height. By contrast, the value of the viscous drag decreases with increasing height, and the reduction rate declines when the size exceeds 4.5 millimeters. So in other words, as we saw before with the riblet, we have in the troughs of the riblets a lower wall shear stress, which means a lower local friction drag. At the peak, we get an increase in the friction drag, but they average out to be a reduction in the drag overall, the friction drag. Now, for these riblets, as long as they're not ridiculously big, they will get a reduction in the drag. As they get ridiculously big, then you don't get a reduction in the drag. So they have here, when the riblets were 1.5 millimeters or lower, the total drag is still reduced by 1.5% or less. At 4.5 millimeter heights or greater, the total drag now is much greater, and that's because you have an increase in the pressure drag. So they say as the pressure drag of the riblet schemes become a principal component of the total drag at high angles of attack, viscous drag reduction is not up to the task of reducing the total drag, and that's why we get this overall increase in total drag. So in figure 15, we see the pressure coefficients of the riblet schemes and the smooth airfoils at 7-degree angle of attack. The pressure coefficients of the H06 riblets, which is the riblets that are covering 50% of the chord, and their height is 0.6 millimeters. So the pressure coefficient of this particular riblet is slightly higher than that of the original, resulting in a greater lift coefficient. Moreover, this is on the suction surface, by the way. Moreover, the pressure coefficient changes periodically in each riblet because of the pressure differences at the riblet's windward and leeward size. So that's really cool. These graphs, you can see like they're typical pressure coefficient graphs over an airfoil surface. And when you get to the riblet section, you get this like real jaggedy, like very fast jagged line. And that corresponds to these riblets. Now that's only for the really big riblet of 10 millimeters. For the small riblet of 0.6 millimeters, you can still see the jaggedness, but it's very, very small. So it's almost, it's not directly proportional, but it is proportional. So moreover, as the pressure coefficient of the H100 scheme, so riblets of 10 millimeter height, is the same as the original, as a smooth airfoil at most of the, along most of the surface, the reduction at 25% of the chord to 41% of the chord on the suction side is the main reason for the decline in the lift coefficient. So in other words, these riblets, that's actually where the riblets are. So for this very big riblet size of 10 millimeters, the pressure coefficient is actually worse. So you're not getting as much lift compared to the smooth airfoil. So that's why they're detrimental. Finally, in figure 17, we look at some flow vis, effectively in CFD. Figure 17 shows the streamlines and pressure distributions of the 3 schemes in the riblets at different locations, sorry, at the same locations. They have them at, for riblets of 1.5 millimeters, 4.5 millimeters, and 10 millimeter heights. Because the trailing separation vortex is not present at this position, so this is along the airfoil about like midway, it is the riblet vortices are still inside the riblets. So in podcast 101, we're talking about how the trailing separation vortex actually sucks out the vortices that the riblets are creating from the riblets and into effectively the vortex and free stream flow eventually. Because in this particular case, there is no trailing separation vortex present, the vortices that the riblets are creating are allowed to just stay where they are and just circulate around. they're inside the troughs of the riblets. What this means is we're actually getting a lower, slower moving flow in this region. That means we have a more shear stress, and that means we have a lower friction drag. So it is noteworthy that the cores of the riblet vortices gradually deviate from the riblet center when the riblet height increases. Or what's more, we also see induced vortices underneath as well. So we have this main vortex, and then this is inducing another vortex underneath in like the very, very trough of the riblet. Now, the larger the height of the riblets, the more eccentric the cores of the riblet vortices are. So, in conclusion, the following conclusions are obtained regarding these riblets. First, the amount of drag reduction considerably varies with the length and height of the riblet at the angle of attack considered. And they also change compared to considering the angle of attack. So when you change the length and height of these riblets, the lift coefficient increase and the drag coefficient changes, and they also change with angle of attack change. When the length exceeds 20% of the chord, the improvement in the aerodynamic performance is nearly proportional to the riblet length. The most efficient riblet length is found to be 80% of the chord, which increases the lift and reduces the drag by 17.5 and 15.1%, respectively. This was at 12 degree angle of attack. So that's huge. That means that the drag ratio is like increasing by 30%. That's massive. On the contrary, the riblets with a length of 5% and 10% are negligible, or even bad for the airfoil. So they're not good. The drag reduction effect is inversely proportional to the riblet height. The most efficient riblet height in this study is 0.6 millimeters. That's also the smallest, by the way. Why would this? So they say it produces an increase in lift and reduction in drag by 12.6% and 40.8% respectively. So why would the smallest riblet be the best? Well, probably because it affects the subboundary layer most. So the subviscous boundary layer, sorry. This helps suppress turbulent formations, and that helps reduce the viscous drag. So, moreover, the riblets with different sizes perform better at large angles of attack than at small angles of attack, especially when considering the riblet height. The drag coefficients of the riblets whose heights exceed 0.6 millimeters are significantly increased at angles of attack below 7 degrees, but they are significantly reduced above that. So, that's the end of this paper, and I thought it was really good. They did a really good job on their CFD. They did a really good job analyzing their results and presenting them. Let me know what you think in the comments below. And if you want to check out podcast on 101, which is the first part of this, make sure to check that out. And if you want to get better at CFD or theory yourself or check out our courses in the description. We have courses for CFD if you want to get better at that, and theory like this. And if you want to make your experiments 2 to 4% more accurate, make sure to measure the density of air in your experiments. Now, this is important because the density of air changes by that much on a regular day. It changes even more between days, weeks, seasons, and months. And they can change up to like 15% between these times. So if you go into your wind tunnel, even during the day, if you go at like 9 a.m., it might be a certain density, 1.2 kilograms per meter cubed. By mid-afternoon, it'll be maybe 1.18, 1.17 kilograms per meter cubed, maybe less or more. If you don't take into account that change, then your experiments have got errors in them and they're not good. And also it means you can't really validate your CFD because your CFD are using a different density as well. So to overcome that problem, we make an instrument called the Atmosphere Hawk. It actually measures the density of air for you, and it gets rid of that error. So now you can be sure that your results are trustworthy. That's in the link in the description, and I'll see you in the next podcast. Peace out, amigos.